All right, so I want to follow up on our discussion of coordinate descent. Okay, so there are many multi-dimensional optimization methods. Okay, and so we've already talked about one-dimensional methods for optimization. So do you guys just remember some of the algorithms we covered for one-dimensional optimization? Okay, so for one-dimensional optimization, we have Newton's method or Newton-Raphson. Okay, and here we just say the next iteration is we take our current value, and then we're going to subtract off the ratio between the derivative and the second derivative, right? And so this is basically similar to root finding, but you're doing root finding for the derivative. Okay, and so when you apply root finding to the derivative, you find the spot where the derivative is equal to 0, which from calculus we know will either be a minimum or a maximum, and then we can test that point to see what value it is. Okay, and then we also did golden section search. Where you have some kind of function, and then and you split it into kind of these chunks, and then you eliminate pieces at a time. Okay. Okay, and then so let me talk about, so as far as multi-dimensional methods, we have coordinate descent. Okay. We also have Nelder-Mead, but I think today we'll just talk about coordinate descent. Let me save this. Okay, and so so imagine we've got some kind of two-dimensional function. Okay, let me you're kidding me. Okay, this is a bummer. Give me a second here. Okay, so imagine we've got some kind of function here. And the function that I'll use is going to be, it's a function of two variables. We got f of x and y, okay, and the function is going to be 5x squared. Oh, sorry. Okay, the 5x squared minus 6xy plus 5y squared. Okay, so this is going to be the function we're going to try to optimize, and so I'm going to plot this in R. Okay, and then so to plot a function like this, basically I'm going to create a function called g. All right, I guess I could call it any other letter. Okay. And so here, this is just basically you plug in the x and you plug in the y, and then it's going to spit back that value for x and y. Okay, and then I'm going to create a sequence of x and y values. So x is currently just a vector of 100 values between negative 1.5 and positive 1.5, and y is also a vector of that, okay? And so I'm going to apply the function outer. Are you guys familiar with outer? Okay, so basically what outer does, so I can say, I'm going to take the values 1 through 10, and I can do outer 1 through 10, comma 1 through 10, and then the default function will be multiplication. So if I do outer 1 through 10, 1 through 10, basically it takes 1 through 10 and 1 through 10, and it creates a matrix that's 10 by 10, and then to calculate the value inside, it applies, by default, it applies multiplication. So here you get a times table, right? But you can also do any other kind of function that you want. So you can do something like outer, you can do 2 through 5 and 1 through 6, and then the function you want to apply is mean or something, which would be kind of a silly function to do. Let's see, trim must be numeric of length 1. All right, I don't know. Let's try. Now it's giving me all sorts of trouble here. Okay, well, on one side we do 2 through 7, and the other side we do 1 through 6. And normally you can do, so let me just create a new function called a, and this function will be a function of x and y, and then what it's going to return is going to return x plus y, okay? So a is just a function of x and y, so if I do a of 3 and 5, it's going to add those two together. So I can do outer 2 through 7, 1 through 6a, and it's basically just adding up 2 through 7 on one side and 1 through 6 on the other side. Okay, so that's what outer does. So basically, I'm just going to apply outer to x and y right here. X, again, is a grid between negative 1 through 5 to positive 1 through 5, and so is y. So outer x and y is going to create a grid of these values, and it's applying the function z. So if I just ask for, maybe the first 5 value, 1 by 5 grid of z, okay? It says if I plug in negative 1.5 and negative 1.5 for x and y, the value that it returns back is 9. And then, and so, and this is what we have. So the dimensions of z, what are the dimensions of z? So look at what we created z with. Z is created with x and y. X has a dimension of 100, or a length of 100, and y has a length of 100. So z itself is 100 by 100. And I've just subsetted just the top corner so I don't print out the whole thing. So I could ask for the dimensions of z, and it's 100 by 100. And if I ask for, what is z, it's a matrix, okay? It's a matrix of class double. You've got 10,000 numbers in it, okay? And so we can plot contour lines, okay? And contour takes three values, right? X, y, and then basically what those values are equal to, and then levels just tells is for me to specify where I want it to draw lines, okay? So here, this is what our function, this is 5x squared minus 6xy plus 5y squared looks like, okay? And so looking at this, we can kind of see where the minimum will be, okay? It's basically this bowl looking thing, okay? It's a bowl with kind of the lowest point right here, okay? And so we can kind of see, just from looking at the picture, it looks like that minimum is going to be at around 0, 0, okay? Which makes sense, okay? We plug in that, you'd get 0. And it seems like anywhere else you'd get a larger value, okay? And so we're going to apply coordinate descent to this thing, okay? So let me, I'm going to just show you what coordinate descent looks like, okay? So this is what our function looks like. And so the way coordinate descent works is you just take a one-dimensional optimization algorithm, okay? So let's say, you pick a corner. So if we start at this corner, well, let's say we start over here, okay? And we're gonna, let's just say we're gonna move in this direction here, okay? So we go along this direction, and we, so let's say this is where y. I don't know. I'm gonna just make up a number. We'll say in this picture. We'll say y is equal to, I don't know, negative 1 or something, okay? So we set, or let's say y equals negative 1.2, okay? So basically, this becomes, if we set y to be a constant, our f of x, our function becomes f of x, where, and then y is set equal to negative 1.2. So now we have a one-dimensional function of f of x squared minus 6 times negative 1.2 x plus 5 times negative 1.2 squared. Okay, so this is just, these are all constants here, and so now I have 1.2 squared is 1.44 times 5, I don't know, is like 7.2 or something. I don't know, 7.2 plus 5x squared plus 7.2x or something like that. Does that make sense? Okay, so I'm just going to optimize this, okay? Optimize for x, okay? And when I do that, I'm going to find kind of the minimum happens to be somewhere like right here, okay? So now let's say this is at x equal to, again, I don't know, negative 0.6 or something like that, okay? So x here is equal to negative 0.6. So now I plug in this and I get f of x equal to negative 0.6, and now it's just a function of y. So I plug in negative 0.6 for all of my values of x. I'm going to have negative 6 times negative 0.6 y plus 5y squared, okay? So this is just a function of y. And I'm going to optimize the function in terms of y, all right? And then we're going to find that the minimum is something like right there, okay? And then now I will optimize in terms of x, okay? So now I have a new constant for y, and I'm going to set that equal to something, and I'm going to optimize, and I'm going to find it's like right here, and then I optimize for x, I find it's like right here, we go for y, and we go over here, or something like this, until we get to the minimum value. Well, we don't know that it's a global minimum. But we know that it'll be a local minimum, and we kind of pick our convergence criterion just to say that if the change between kind of the previous value and this value, the change between the function evaluation is very, very small, we're going to say we've converged. Okay. So basically the altitude change between the previous iteration and this one, if that's really tiny, we're going to say we've done it. Right? Is that okay? And so here we can apply any one-dimensional method. So you could use Newton-Raphson as the one-dimensional optimization method. You can do golden search. It's also very good at picking out the one-dimensional optimum. Okay, and so how would we write a routine in R to handle something like this? Huh? So let's Okay, so basically, so let's say I've got, let's say I have a function called golden. Okay, so golden is going to take, golden will be a function that takes basically an f and basically a lower and an upper bound. Okay, and then what it returns will be equal to the we'll say minimum value in the range. Okay, and then we've got g is a function of x and y, and g of x and y is, what do we say, 5x squared minus 6xy plus 5y squared. All right, so let's say we're going to do coordinate descent for this. Coordinate descent. If I wanted to turn this into coordinate ascent to find the maximum value, what would I do instead? Whatever my coordinate descent algorithm is, I just use the exact same thing, and I just multiply my g of x by -1. Okay, and that will turn it into a maximization algorithm. Okay, so whatever right now we're using it to find the minimum value. Okay, but if you want to use it to find the maximum value, you just take whatever function you're trying to maximize. Okay. You multiply it by -1, and then you find the minimum of that, and that's going to be the opposite. Okay, you don't have to work out any other mystery thing. Just do that. Okay, this is a very useful thing. So if someone has a sorting algorithm that will sort from least to greatest, but now they want you to sort it from greatest to least, you don't have to do anything. Just take all of your input values, multiply it by -1, sort it from least to greatest, and then at the end multiply those by -1 again. Okay, and then it'll be greatest to least. Okay, that's like the fastest way if you wanted to change the order. Just multiply everything by -1, apply the thing, and then undo that -1 thing. Okay, it's a nice thing. Okay, so let's say we want to do coordinate descent. All right, so what should we do inside our loop? Okay, so our coordinate descent will have basically, we're going to take in a function, and then basically we'll have a starting x and a start y. And then so we'll say we'll set y equal to start y, right? Okay, all right. And then so what we're going to do here is we're going to basically have to create a new function. Okay, so we'll call this g sub x. Okay, and this is going to be it's going to be a function where we're going to take, it's going to be a function of x, right? And the value we're going to return is going to be g of x, where y is equal to start y. Okay, so we have to create a new function here, g sub x. Okay, and then we're going to apply golden to this. Of this new function, and then you have your lower and upper bound, and this is going to be kind of whatever this turns out to be will be our next x value. And then now we set x equal to the next x value, And then you're going to have a g sub y, where you get a function of y, where you're going to plug in g of x equal to next x, and you get a y. Okay, and then you apply golden to this, golden of g sub y, the lower and upper, and what this returns will be our next y. Does this make sense? Okay, and then basically we put this all inside some kind of loop. Okay, so you put this in a loop. Okay, so you'll need something for a convergence thing, right? So maybe we can create a while loop, and we'll say basically while maybe the difference is greater than some tolerance value. Okay, and then the difference will now be basically, we have to set difference equal to the difference between, you know, g of basically start x and start y, or old x and old y, minus g of the next x and next y. Okay, and that's a very kind of a loose representation of how the coordinate descent algorithm will work. Yeah.
Sorry, what's the word that's next to the bracket?
Loop. Yeah. So you can put this in a while loop, where, you know, as long as the difference is greater than the tolerance, keep doing it, and then that should work. Okay. So of course, the actual code will be a little bit more complicated than this, but it can be done. All right. Okay, is that all right? So if I put this as part of your homework to write a coordinate descent, we can kind of do it. Of course, it'll be a little bit more work than just kind of what I have. This is just kind of you know, pseudo code that won't actually run, but there's something like that. So inside the function, so inside the loop, you have to redefine new functions of x and y, if that makes sense, right? Because that's effectively what we're doing. And then you, after you've defined that new function, you put that in the golden function. So as part of your homework, I will give you code for golden section search. Okay. The book, our textbook, also has one. I have another code that maybe I like a little bit more, but it'll work. Okay. And then you apply it to something like this. All right, so that's kind of an outline there. All right, I want to start talking about probabilities and simulating maybe random variables in R, and then we could use that to kind of build up more complicated simulations. Okay. So pretty much almost we can simulate pretty much any random variable as basically as an alteration basically uniform 0, 1. Okay, so we're going to you can look up all of this, but we're going to assume our computer can create, simulate values from a random uniform distribution from 0 to 1, okay? And this used to not be, so from 0 to 1, all of these values have, all values between 0 and 1 are equally likely to be simulated, and we can do this, all right? And then so this in R is just R unif, and you ask for how many values you want, you give you 1, okay? We'll return one random value between 0 and 1. Okay. R uses the, we have what we call pseudo-random number generators. In computational statistics, this used to be a big topic where people discussed the qualities and properties of pseudo-random number generators, right? Because you know, there's kind of this question of what's truly random in the world. You know, are coin flips truly random? You know, for most purposes they are, but they're not. They're just you know, if you could know the exact velocity and force applied to the coin, you might be able to calculate exactly how, you know, whether it should land heads or tails, right? If you knew exactly all of the forces applied to the coin, and you know, the property of the table and how it lands and all of that, maybe we could figure this out. You know, maybe at some quantum level there's true randomness, and you do have true random systems that try to get numbers, random numbers from, I don't know, different natural sources of randomness. You know, in the computer, we write programs to write up random numbers, and there's this question of, you know, are these really random numbers? It's a tough question, okay? Now, but we have developed very good, high-quality pseudo-random number generators, okay? And you can, you know, in your leisure time, you can look up videos, look up random number generation in Wikipedia or watch YouTube videos on this. You have, R uses what's known as the Mersenne twist. Or twister algorithm. I used to know how it works, but I forget. It uses Mersenne primes to try to generate numbers and modulo arithmetic and things like that. So, you know, basically, we can consider the problem of random number generation almost as a solved problem, where we don't really have to worry about what exactly is going on, okay? Just like back in the day, if you wanted to learn computer programming, you had to learn things in almost like assembly, okay? And now we don't really teach that, okay? You had to learn how to manipulate bits and ones and zeros, and now we don't bother with that. We just teach you higher level languages like R or Python or things like that. And we don't bother wasting our mental energy on random number generation anymore, okay? So we're gonna just say, like, this is pretty good, okay? Not cryptography good, but this is pretty good, okay? So basically, if you generate a bunch of random numbers from the Mersenne twister, it's you're going to and you look at the density of this, you're going to get something between 0 and 1, okay, with very little patterns, okay? So we'll show no patterns, and the numbers generated will have similar properties to what we would expect. Okay, but it's not cryptographically secure, in that if you were to use this to generate crypto codes, then somebody could crack it. So they have other algorithms for that. But as far as random number generation, we're good. Okay, so basically we can simulate values between 0 and 1. Okay, so we're going to take that as a given. Okay, so we can ask R for R unif 1, and it will give us a random number between 0 and 1. Okay, let's say we want to use this to simulate another probability distribution. Okay, so there's all sorts of stuff, okay, that we can do. All right, are we familiar with the binomial distribution? Okay, so someone explain to me what the binomial distribution is.
Well, it's used for when you know how many trials there are. Or something.
Okay, yeah, so we have n trials.
And then the probability of success on any trial.
Yeah, so
is
each
P.
trial has p. P is probability of success for each trial. Okay, and then x is basically the number of successes we want. Okay, so let's say I want a binomial distribution with n equal to 3 and p equal to 0.5. Okay, so my outcome x, I'm going to create a table, and probability of x can be anywhere between 0, 1, 2, 3, 0, 1, 2, or 3, right? Okay, what would the probability of 0 be? So it would be, 3 choose 0, 0.5 to the 0 times 0.5 to the 3. Huh? So this becomes just 0.5 to the 3, we get 0.125. It's okay? Right, so probability of x is n choose x, p to the x, and 1 minus p to the n minus x. I'm hoping this is okay, or do I need to review this? We're okay? All right. And then, okay, so then for probability 1, we would have 3 choose 1, 0.5 to the 1, 0.5 squared, and we get 0.375, okay? This probability for 2 is 0.375, and probability for 3 is 0.125. Okay. So my probability mass function, is it okay that I'm doing this, or are we... okay, we have 0, 1, 2, 3. My PMF looks like this. Oops. Okay, this is my probability mass function. I have a cumulative mass function. Okay, what's the cumulative mass function?
That's where for each one you sum that and all x values below it.
Exactly. So we sum everything and everything below it. So we go 0, 1, 2, 3, okay? And so the range of the cumulative mass function goes from 0 to what? 0 to 1, okay? So the highest value will be at 0 equal 1, and we know that at 3, we're going to be at 1, okay? And then so at 0, we jump up from okay, so we're going to, when we get to 0, we're going to jump up to 0.125. And then we go up to 1, and then when we get to 1, we jump up to 0.5. And then at 2, we jump up to 0.875. And then at 3, we finish it off, 0.125, okay? Or to 1, okay? So the height of this, so at 0, below 0, we're we have probability 0. So our cumulative mass function goes like this. So at 0, we jump up to 0.125. At 1, we jump up to 0.5. Here we're at 0.875. And 3, we're at 1. Okay. So essentially, we're going to look at this cumulative mass function. And we're going to use this to go from a random uniform on 0, 1 to generating our binomial distribution. Okay, so let's show you how this would work. Okay. So effectively, let me just I'm going to we're going to take some value. We'll just call this u. U is going to be a random number between 0 and 1. Okay? So basically I can generate from 0 to 1 with equal probability. And effectively, the rules, this is at a practical level, this is what we're going to say. Basically, if u is between, or we'll say if 0 is in between u and, or if u is in between 0 and 0.125, then x is going to be equal to 0. Okay, so if the random number we get is between 0 and 0.125, x will be equal to 0. All right, and if the random number we generate is between 0.125 and 0.5, then x will equal 1, right? And if 0.5 is, if u is between 0.5 and 0.875, then x is 2. And if 0.875, if u is between that and 1, then x will equal 3. Okay, and so if we look at that, we can see it's now easy to see that then it will be clear, or I hope then it is clear that x has the following probabilities. which will be x can be 0, 1, 2, or 3. And the probability of x, what's the probability that x is going to be 0? It's going to be the probability that u ends up between 0 and 0.125, which is 0.125. The probability of x being 1 is going to be the probability that u ends up between 0.5 and 0.125, which is 0.375. And applying that, we see that x will have these probabilities. Okay? And if x has these probabilities, then that means x comes from binomial with n equal to 3 and p equal to 0.5. So before I go on, I just want to make sure this process makes sense. That by taking the cumulative mass function, I can say that if our uniform variable ends up between here and here, then x will take on this value, right? And if I say that, then that means the probability that x takes on any one particular value. What's the probability that x is going to equal 2? Well, that's the probability that u ends up being between 0.85 and 0.875, which in this case is 0.375. Then that's going to be the probability of x. And if x has these probabilities, then that means x comes from this binomial distribution. Is that okay? All right, so how can we write this in code? Okay. So here's one way to do it. Okay. So first we're going to create basically the f function. Okay. So we're going to okay, so we'll have a function capital F, okay, and what capital F is basically capital F is the cumulative mass function, okay. And so when we ask for the function capital F of x, it will return, 0.125, 0.5, 0.875, or 1, okay? So f is basically, we're going to ask just for, what's the value of 0, what is this thing, okay? And it's going to return, it's going to return whatever this is, okay? So for this, we can say so this will be a function of x, n, and p, okay? And so basically, if we plug in 0, what we want is we're going to calculate and choose. We're going to calculate n choose x, times p to the x times 1 minus p raised to the n minus x. Okay. And so what we're going to do is we're going to start off with the value. Okay. So initialize, we'll say f of x, we're going to start off as equal to 0, okay? And then what we're going to do is we're going to say, we're going to create a loop for I in basically 0 to the x, okay? And we're going to modify f of x to be equal to f of x plus basically the binomial probability, which is going to be basically choose n comma I times p to the I times 1 minus p to the n minus I, okay? So we put this inside here, and then we return f of x.
So it's making the steps.
Yeah, so this will make the step, okay? This will make the steps. So let me, here, I'll type this out. Okay, so we'll call this cumulative mass function will be a function of x, n, and p. And in this function, we're going to start off with set f of x equal to 0, okay? And we'll build a loop for I in 0 through x, whatever x we've specified in the function, right? And we're going to take, so initially we start off with 0. We're going to do 0 plus, and we're going to start off with choose, n choose 0 times p raised to the I, whoops, times 1 minus p raised to the n minus I. Okay, so we start this off, it's going to start off with 0 plus, choose n 0, n choose 0, p to the 0, 1 minus p to the n, and then it calculates that, and then it loops around and it does choose n2 and so on and so forth, okay? And then when we're done, we return fx, okay? This can also be written in vector form, right? We could just, we could say, basically apply a vector and then do a sum on that, okay? So, you know, however you want to do it. Okay, so this will create our steps, okay? Did I forget to close this off? What's going on? What's going on? Did your thing break? Huh? All right. Let me, just reset my session here. All right, I don't know what's going on. Okay. So that's our cumulative mass function. So that's going to create the steps, okay? And then for the CDF, okay, I'm sorry, to simulate what we're going to do, we're going to create a function, and this function is going to take on basically our function, the f function, and we're going to use the dot dot dot, okay? And what the dot 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 does is pass additional arguments. Okay, and so this function takes x, n, and p, and inside our function we're going to use the x, but then we're going to pass it the n and the p, okay? So inside this function, we're going to start off with x equal to 0, okay? And then we're going to simulate a random variable. We're going to just, or a random number between 0 and 1. And then what we're going to do is we're going to say basically while the value of f at that particular x, not x equal to 0, sorry, f of x, okay, if it's less than u, then go x, we're going to increase x by 1. And then at the end, we'll return our x, okay? And then we close off our loop here. All right, so what's going to happen here is we're going to start off with x equal to 0, okay? And then we're going to see is f of x, is this function, is the step for 0, is that less than our u, okay? And if it's not, then we're going to return x, okay? So let's say u ends up being 0.05, okay? So then that means we should be returning x equal to 0. So if u is 0.05, we're going to look at this. We're going to start off with x equal to 0. We're going to say is f of x less than 0.05, okay? So f of 0 is 0.125. 0.125 is not less than that, so we don't run this loop, and then we just return 0, okay? On the other hand, let's say x is, our u ends up being 0.7, okay? At 0.7, what the number we should be returning is 2, okay? So we're going to start off here. We say is x equal to 0. We're going to say x is 0. What's f of x? F of x is 0.125. Is 0.125 less than 0.7? Yes. So we run it, and then we say, try it again with x equal to 1. Is f of x, f of 1, which is 0.5, is that less than 0.7? Yes. Okay, try it again. Now try it with 2. At 2, our f of x is 0.875, okay? Is 0.875 less than 0.7? No. Then we return x, which is 2. Right? Does that make sense? So we, start at x equal to 0. Check to see, the loop is check to see if basically the step value for that x is less than the random uniform number, okay? If so, increment x, otherwise return x. Okay, let me see if this will work. All right, my RStudio is not working. Can't even kill it. All right, let me stop the video.